Nick. I'm working in Canonical as a security engineer, and today I'll be presenting to you my work in my master's thesis in UCL about defending against data poisoning attacks in federated learning via user elimination. So this summit is all about getting the most out of machine learning, and we've heard some great talks yesterday, more to come today. And I think the gist of all of it is that the rise of machine learning solutions is directly linked with two things: the explosion of data availability and the explosion of computing power. But what happens if this data is not widely available? And as we all know, the optimal solution to that is federated learning. And one of the best interpretations of it is this code right here, that it brings the code to the data instead of bringing the data to the code, which I think was very, very smart. So what could go wrong? I mean, letting users train a global model seems like a great idea, but when all of them are honest and without malicious intentions. But this is not always the case, as we can have users that try to harm or take advantage of our model while participating in the training process. And for the rest of this presentation, we're going to examine the privacy concerns that happen due to uncontrolled user participation in federated learning. We're going to present an attack that threatens the viability of such models, and we're going to come up with a robust defense that successfully tackles those attacks. So let's talk a bit about those attacks. We're dealing with users whose goal is to harm our models in a targeted and predefined way. They are trying to mislead the model to misclassify a specific class as another. And a simple solution to that would be to take a look in the training phase and catch those attackers when trying to submit false data. But as we know, in federated, that's very difficult because data is being kept local. So which metrics are we going to use in order to detect them? We opted to use accuracy, cross entropy loss, and a less common one, which is source class recall, which is the number of correct positive predictions that were made out of all positive predictions that could have been made for a specific class. So let's take a look at the results of launching a data poisoning attack. As we can see, the overall accuracy and loss of the models remain in satisfactory levels throughout our experiments. And in a real-world scenario, when we have only one of those models, it would be very difficult to distinguish that it's been under attack because, for example, that could happen because of, I don't know, like poor tuning of the model. However, the ability to distinguish malicious participants due to their higher produced loss is a very interesting observation. As we said, we need another metric to try to detect them, and this is source class recall. And as we can see, for the first two attacks, 10 and 20%, they are following the curve, but when we go closer to 50%, it hardly differs from zero, which is completely different from the other two metrics. So we try to think outside of the box when it comes to ideas in defending against poisoning in federated learning. Relevant work indicates that users only should report back their gradients, but we opted to make them return the training loss for the local training round. And we assume this produced by attackers will significantly differ from the ones produced by honest users. And however, if a user reports the exact value of the training loss, it could be bad because adversaries could extract useful information for their training and thus harming the federated learning promise for privacy. So to avoid that, we used local differential privacy by having a layer of injecting a random amount of noise in every reported loss. So let's take a look here at the algorithm that we have. We start for the global update. We select, as always, a random portion of the users for training. We send them the global model, they receive it. We keep track of the training loss as well. We add random noise from a non-LDP distribution, and we report back a tuple of the gradients and the noisy loss. This is then received by the server, and we call an elimination algorithm. In our case, we chose to use k-means by defining two clusters in which malicious and honest clients were full. And after that, we eliminate the selected users from a global update, and we aggregate only the honest gradients. And this is one epoch of our training. So the results. The first aspect we care about, of course, is the final performance of our model. As we can see in both the first plots, the results are very satisfying. This is the source class recall and the accuracy. But even with 40% of the users being malicious, our defense ensures a minimal deviation from the performance of the honest model. And as we can see in our third graph, which is how the model behaves with and without our defense, we have a significantly better source class recall. And we are able to confirm that we can safely and efficiently train a model without harming either its utility or its robustness. And another aspect that we wanted to make sure is that we are correctly capturing the attackers and not honest users. And our metric in this case is attacker detection accuracy and F1 score. And we can observe from the two plots that we have satisfactory performance in MNIST and CIFAR-10, which is the two datasets of our experiments, for up to 30% of malicious user presence. And we're maintaining a 55%, over 55% of accuracy, even in the most extreme conditions, where half of the users are malicious, and we are training in CIFAR-10, which is a hard data set. So, in conclusion, what we did was we tried to tackle the challenge of data poisoning attacks in federated learning, where attackers can subtly alter a model's behavior without hurting its accuracy. Our defense identified the malicious users by the reported loss values, all while preserving both model efficiency and privacy. To preserve that privacy, we did use local differential privacy by inserting a layer of random noise. And then we use the k-means clustering algorithm to separate the honest users from the malicious ones. And this method was tested on MNIST and CIFAR-10, showing strong results in both. And I think most importantly, this is an approach that is flexible. It can adapt to various attack scenarios as long as the local training loss is increased every time by the malicious attackers. And this is making it a promising direction for securing federated learning systems in general. And finally, those two QR codes can give you access both to the full paper and to the open source code of our experiments. And yeah, that's it. Thank you.
Thank you so much, Nick. Do we have any questions? Yes, over there. Oh, quite a few. All right. I think we have some time, so...
Well, thanks for the great talk. Yeah, I really like this view of the loss value. Maybe I'm kicking in an open door, but if the user is willing to find malicious data for the model, why not will it find the malicious value for the loss function? I mean, if you have a detection mechanism based on a loss value, I could just engineer data that has a certain loss value.
That's a great question. Yeah, thank you. So in the full paper, we actually try to tackle that. So this is a scenario where we trust the users. If we don't trust the users that they will introduce the correct loss values, then it is a trade-off, and we need to have some more computational power to do that. There are methods that we can try to catch that. We name in the paper range zero knowledge proofs to do that. Essentially, we are taking data from the last epoch and define it as the one that we are trusting, and this is the range of the zero knowledge proof that can the user is allowed to return the loss into, and they have to prove it with a zero knowledge proof. But yeah, this introduces a bit of an overhead. So in the default example that I presented here, we don't have it, but in general we do have it. Yeah, thank you for the question.
Okay, cool, thanks.